So the first example is saying the strings of length at least 2. That means at least the string of length should be 2, and we can have any string whose length is greater than 2. That means we can have a string of length 3, we can have a string of length 4, we can have a string of length 5, and so on. So we can say we can have string of length 2, and then we can have any length string. So this can be represented by, this is string of length 2, a plus b concatenated with a plus b. String of length 2 is now concatenated with a plus b star. A plus b concatenated with a plus b is concatenated with a plus b star, and this is representing string of length 2, and we can have any length after that. If you can open it, you can see we can have all the strings of length at least 2. Next is a raised power n, b raised power m, such that n comma m is greater than or equal to 1, and here it is representing a raised power n, b raised power m, such that n comma m is greater than or equal to 0. What is the difference between these two examples? See, in the first example here, a raised power n, b raised power m, and where n comma m is greater than or equal to 1, so at least the minimum length we can get is ab, we can have abb, we can have a triple b, and so on. We can have any number of b's, we can have a, ab, we can have triple ab, and we can have any number of a's, and so on. The only thing which we cannot have is any combination of a's and b's. This language is actually representing all the strings should start with a and end with b, but as soon as we get one b, then we should get a continuous run of b's. That means in the starting we can have any number of a's, and as soon as we get one b, we can have any number of b's, and a and b are not dependent on each other, and the minimum length should be 1, or you can say should be 2. Number of a's should be at least 1, number of b's should be at least 1, therefore the minimum length can be 2. Okay, and this is representing strings of length where n comma m is greater than or equal to 0. The only difference between this and this one is, in this case AB is of length 2, but here we can have a string which is of length 0. So we can have this epsilon, we can have single a, we can have AA, we can have AAA or any number of a's, we can have single b, we can have BB, we can have any number of b's, and so on. Or we can have, initially we can have any number of a's and then any number of b's, and so on. Okay, now here in this case the only difference between these two is here n comma m can be greater than or equal to 0, and here n comma m should be greater than or equal to 1. That means in the above case at least one a or one b should be there. Right, this creates a huge difference between these two languages. So you can see here you get so many strings which are extra, which are not present here. Okay, now the regular expression for this is very simple. This language actually can be represented by a star, b star, and star does not make them equivalent to each other. Star means we can have any combination of a's, or we can have any combination of b's. Right, that means initially we get a, and as soon as we get one b, then we'll always be getting b's. We cannot get b's, and this a star dot b star is not equivalent to a plus b whole star. That means what I'm saying is, if I'm writing a star b star, it is not at all equivalent to a plus b whole star, and it is also not at all equivalent to ab whole star. You can say a star b star is not at all equivalent to ab whole star. When I'm saying ab whole star, that means it will be multiple of ab. So here if I'm saying ab whole star, it means the strings can be epsilon, it can be ab, it can be ab, it can be ab, and so on. But here it is representing a different set of strings. It is representing epsilon, a, b, a, b, b, and so on. But here we cannot have a, b, b, and so on. So these two are not equal. Okay, keep this in mind. And here I'm saying the length should be at least 1. So this language can also be represented like this. It is a dot a star and b dot b star, or the better way of representing is a plus concatenated with b plus. And a plus b plus does not make a and b as equivalent. They may be equal, they may not be equal. It can happen, right? So this is representing A plus dot B plus. This is representing A star dot B star. And when I'm taking this one, this is A raised to power A star, B star, C star, right? So because length is greater than or equal to 0, so it can be represented by A star concatenated with B star concatenated with C star. So this is a regular expression which is representing the complete language, all the possible strings of the language, right? So any regular expression which we should give, that should represent all the possible strings over any given language. Okay, fine. Now if you take this example here, the length should be at least 1. So either you can represent it like this: A concatenated with A star, B concatenated with B star, C concatenated with C star, or you can represent it like this: A star concatenated with A, or B star concatenated with B, or C star concatenated with C, or you can take A plus dot B plus dot C plus, or you can make any combinations of this like this. We have A concatenated with A star, B plus, we have C star concatenated with C. You can make it like this also. There are different several possible representations of a given language which is possible, right? We have seen these examples before. Now the next one is we have A raised to power n, B raised to power n. Now can you make a regular expression for this? Is it actually possible? Where n is greater than or equal to 0. You need to understand, when I'm saying A raised to power n, B raised to power n, this language is not at all equivalent to this language. It is not at all equivalent. A big no. A big no. They are not equivalent. Why? Because here number of A's and number of B's may not be equal, but here in this case number of A's and number of B's both are equal. And these two are not representing the same language. Got it? So they are not at all representing the same language. Fine. So by the way, for this language you can give a regular expression, which you will know at a later part of time. Just let me tell you here that this language is not at all regular, because here we have a comparison between A's and B's. Number of A's should be equal to the number of B's, right? But in case of finite automata, we cannot draw a finite automata for this language, right? Let me know if you can draw a finite automata, because the biggest award in computer science is the Turing Award. Turing Award is on the scientist which is Alan Turing, who you can say the inventor of Turing machine. But here A raised to power n, B raised to power n is not at all regular. We cannot make a finite automata. If it is not regular, how can you give a regular expression? Therefore, you cannot give a regular expression for this language. In the same way, you cannot give a regular expression for this language. A raised to power n, B raised to power n, C A raised to power n, B raised to power n. Even if you have a language which is A raised to power n, B raised to power n, C raised to power n, such that n is greater than or equal to 0, you can give a regular expression for this language, because this language is not regular. But if you take a regular language like this, A raised to power n, B raised to power n, C raised to power n, such that n is less than or equal to 10 raised to power 10 raised to power 10 raised to power 10. Now this language is regular and you can give a regular expression for this. We will discuss this, don't worry. We will be discussing something called as pumping lemma. In case of pumping lemma, we will be seeing what are the properties of regular language, or how can you say a language is regular. Or in rough sense, right now I can say that if you can give a finite automata for any language, that language is called regular. If you cannot give a finite automata, then that language is not regular. For this language, you cannot give a finite automata. But for this language, you can give a finite automata which will be containing number of states accordingly. Okay, right. So let us see few more examples of what are the few more examples of regular expression. Maybe I can take few more examples of the languages for which you cannot make a regular expression because they may not be regular. Right. So we'll be seeing what are the other types of languages after we study the pushdown automata and this Turing machine. Okay.